produce a lot of work or publication. Apart from that, the lecturers here was very friendly and always motivated their students to study enthusiastically and achieve their goals. The curriculum that I chose was by course. Considering that I am a fresh graduate who has not worked yet, so my time to attend lectures here has become more flexible. Thus, I can develop existing knowledge so that later I can apply it in my life.
Hi, my name is Kartini Putri Ulandari and I am one of student of Mathematics Master at Airlangga University who takes a research curriculum. I think in this curriculum, we are given more flexible time of lecture because in this curriculum is designed for someone who has job and a lot of activities who does not have to attend the lecture. And now, I'm already work at the PT Bank Mandiri. However, this curriculum is perfect for me who has already have a job and already have a family. So that I have a flexible time to work and study master degree and to have time with my family. Moreover, there are still a few universities that have opened the master study program with research curriculum.
The study program offers 5 areas of interest, namely analysis and geometry, algebra and combinatoric, system modeling, operation research and computation, and statistics. The study program has facilities that meet national and international standards, including cool lecture rooms, laboratories, discussion room, reading room with textbook and journal, Wi-Fi, and software.
The Master of Mathematics study program at Airlangga University is committed to producing graduates who are able to meet the demand of the time as a dynamic for achieving better quality education.
For those of you who prioritize quality, please come join with us. Register yourself as a student of Mathematics Master Study Program Airlangga University, Indonesia. We offer proof, not promises. The Mathematics Master Study Program Airlangga University, Indonesia. Mathematics, develop life science and technology. Thank you. Wassalamualaikum warahmatullahi wabarakatuh. Mathematics Master Study Program Airlangga University. Mathematics, develop life science and technology.
Terus aku ngarep
Welcome to the undergraduate program of Mathematics, Department of Mathematics, Faculty of Science and Technology, University of Airlangga. Operating since 1982, the undergraduate program of Mathematics University of Airlangga has a vision to be a leading study program in Indonesia and recognized at the regional level in the development of mathematics and its application, especially in the field of life sciences and industry, as well as play a role in the development of a scientific community that has religious morality. In achieving this vision, the undergraduate program of Mathematics University of Airlangga has missions: manage learning and teaching excellence in mathematics and its application, supported by competent resources; participate in the development of research in the field of mathematics and application that support the improvement of the quality of education, knowledge, and social welfare. Conduct community service activities in the field of mathematics and its application through mutually reinforcing cooperation with the elements of society, industry, and education. At this time, the undergraduate program of Mathematics University of Erlangga had obtained ASIN accreditation from BINPT. There are 4 scientific fields in the undergraduate program of Mathematics University of Erlangga, including algebra, analysis, systems modeling, also operation and computing research. As the primary means of learning, the mathematics department classroom have been equipped with an LCD projector and a large room capacity. Besides that, the mathematics department also has a computer laboratory to support learning in the form of practice. The undergraduate program of Mathematics University of Erlangga is classified as active in participating in conferences and competition, such as scientific writing competition, the student creativity program, etc. Not infrequently, students in mathematics have won awards in international competitions. In addition to honing academic skills, there are also media to hone students' non-academic abilities through activities held by mathematics students' organizations of Himatika, such as MLC Math and Logic Competition, Himatika Mengabdi, Himatika Balance, Community, API, magazines, etc. Go ahead and do your work and achievement in the Faculty of Science and Technology undergraduate program of Mathematics University of Erlangga.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Salam.
Good afternoon, ladies and gentlemen. Welcome to today's system modeling guest lecture with the theme Exploring Global Stability, Mathematical Insight and Case Study in This is Dynamics. My name is Muhammad Akbar, and I am honored to serve as your Master of Ceremony this afternoon. First of all, let us express our gratitude to Allah Subhanahu wa Ta'ala for His blessings and grace that allows us to gather here today in good health and condition.
Alhamdulillah.
It is my pleasure to extend a warm welcome to all distinguished guests, especially Professor Dr. Fatmawati, Master of Science, Vice Dean 3 of the Faculty of Science Technology, our esteemed speaker, Dr. Omowumi Fatimah Lawal. Hello, Doctor.
Hi, thank you.
And also our moderator, Mr. Rudianto Artiono, Master of Science, as well as respected lecturers, committee members, and all participants joining us today. To begin today's academic session, we will proceed with the opening ceremony. Ladies and gentlemen, to show our respect and love for our nation, let us rise and sing together the Indonesian national anthem, Indonesia Raya. Thank you very much. Next, we will listen to the opening remarks delivered by Professor Dr. Fatmawati, Master of Science, Vice Dean 3 of the Faculty of Science and Technology. To Professor Dr. Fatmawati, we can invite you to deliver the remarks.
Okay, thank you, Mas Akbar. My voice is clear?
Yes, Prof.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests, Dr. Fatima Lawal. Hello, Dr. Fatima. How are you?
I'm fine, thank you, Prof. Good morning, Ma'am.
Okay. Okay, Dr. Fatima from Bamidele, Olumilua University of Education, Science and Technology, Nigeria. Dear lecturer, student, and all guests, good afternoon, ladies and gentlemen. First of all, I would like to express my gratitude to all of the participants and distinguished guests for their contribution to the online guest lecture with the title Exploring Global Stability, Mathematical Insight and Case Studies in Disease Dynamics. I hope that all of the participants here will find a lot of experience and knowledge about the application of infectious disease modeling in the real life. Ladies and gentlemen, Universitas Airlangga, especially Faculty of Science and Technology, will continue to move quickly to increase the internationalization program. One of them is by continuing to collaborate with partners, universities from abroad, and adding new partners. One of the programs to enhance collaboration with academic excellence is the Inbound Staff Program, the activities of which can currently include guest lectures. Ladies and gentlemen, by this online guest lecture, I hope students and lecturers have the opportunity to learn directly from the world-class researcher. Finally, I would like to wish the online guest lecture had great success. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam
warahmatullahi
warahmatullahi
wabarakatuh.
wabarakatuh.
Thank you very much, Professor Fatmawati, for the valuable and encouraging remarks. Ladies and gentlemen, we will now continue with the opening speech and introduction of our guest speaker, which will be led by today's moderator, Mr. Rodianto Artiono. to Mr. Radianto. The floor is yours.
Thank you so much.
I think a little bit lagging.
Better now?
Yes.
All right. Okay. Thank you. All right. Okay. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
All right. Okay. Very warm welcome to all of you. Thank you so much for joining us today, and your enthusiasm and presence means a lot for us. Right. First of all, I also would like to introduce myself. My name is Rudianto Artiono, and I will be serving as the moderator for our afternoon guest lecture. I'm truly honored to present our distinguished guest speaker, Omohumi Fatimah Lawal PSG from the Department of Mathematical Sciences, Bamidele Olumilua University of Education, Science and Technology, Ikire, Ekiti, PMB 250, Ekiti State, Nigeria. Hopefully I pronounced it right. So before we begin the lecture, allow me to read short version of Dr. Lawal curriculum vitae. Here we have Dr. Lawal is a mathematician with research interests mainly focused on computational mathematics, data science, dynamical system, mathematical biology, mathematical ecology, mathematical epidemiology, mathematical modeling, and also optimal control theory. She earned her bachelor degree in mathematics education with second-class honor upper division, December 2005, with project title Factor Responsible for Student Lack of Interest in Mathematics in Some Selected Secondary School in Ilorin, and master degree in Technology in Mathematical Sciences, PhD grade, June 2017, with dissertation title Interior and Exterior Penalty Function Method for Optimal Control Problem Constrained by Ordinary Differential Equation. And she got her PhD in Mathematics, October 2024, with thesis title Mathematical Modeling of Diploid Fever Transmission Dynamic with Optimal Control Strategies from Federal University of Technology, Akur, Ondo State, Nigeria. She has author and co-author numerous publications in reputable journal and has been actively engaged in advancing mathematical approach to public health problem, particularly in infectious disease modeling, and her work highlight the use of nonlinear dynamical system to understand disease transmission and control strategies. Right, okay. And today, she will deliver a lecture entitled Exploring Global Stability, Mathematical Insight, and Case Studies in Disease Dynamics. Right, okay, before we begin, let's have a little chat with her. Dr. Lawal, how are you today?
I'm fine, thank you.
All right, great. I just wonder, what time is it now in your country, Dr. Lawal?
You
Is it
said
too early for you? What time is it now?
7 a.m. We are 10 minutes past 7 now.
All right,
In the
okay. Hopefully it's
morning.
not so early for you.
Not at
Okay,
all.
thank you.
It's fine.
Great, thank you.
You're welcome, sir.
Dr. Lawal, you have 1 hour to do presentation and about 50 minutes to do Q&A session. Is that okay for you?
It's okay.
All right, okay, thank you. So without further delay, please welcome Omohumi Fatimah Lawal PSG. The screen is yours, doctor. Do you want to share your screen or we will share for you, Dr. Lawal?
Either which one will you prefer? If I can share from my hand, it's okay. If you want to share for me, it's also okay.
Okay, maybe we try with your first, and if you have problem, then we will replace the presentation. Is that okay?
Okay, sir.
All right. Okay. Thank you, Doctor.
You're welcome. So can I start now?
Yeah. You can start now, Dr. Lawal.
Okay. Sorry. So, Assalamu alaikum wa rahmatullahi wa barakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
I'm here to give a lecture titled Exploring Global Stability, Mathematical Insight and Case Studies in Disease Dynamics. Mathematical modeling is the process of converting real-life problems to mathematical equations through model formulation, and over the last centuries, many mathematical models have been developed to describe the various dynamical systems. So by dynamical system, we mean system that changes with respect to time, and it obeys a fixed rule. That is the ordinary differential equation rule. And it could be non-linear and it could be linear. When we say non-linear, are those ones that involve multiplication power, like the equation given when we have the rate of change of s with respect to t, which is equal to minus beta si, where s and the I are the state variables. Then what we call state variables is when we divide the total population that we are considering into different compartments. So each compartment is, the variables there are called the state variables. So the product there makes it non-linear, while the linear one is the when you have the rate of change of x with respect to c as the first equation given there, where we have 3x plus 2y minus 6. That is linear equation. But generally, most human real life problems are non-linear in nature. They are non-linear dynamical system. So numerous compartmental models have been developed and widely used to describe the spread of infectious diseases, and we have the common one like the SIR, the S. Sir, are you talking to me?
No, it's okay. Just go on, Dr. Lawal. It's okay.
Okay. Like the SIR, SEIR are the compartmental model that we have. So after developing models, there's a need for you to carry out qualitative analysis and quantitative analysis. So some of the qualitative analysis that is mostly carried out in modeling includes the possibility and boldness of solution, equilibria. That means we mean the disease-free equilibrium and endemic equilibrium. Then the basic reproduction number and other threshold parameters. Then local stability analysis of equilibrium, the global stability analysis, which is one of our main focus for today, then the bifurcation analysis, the sensitivity analysis, and many other analyses have been carried out on every developed model. This talk largely focus on examining the qualitative behavior of compartmental models, specifically the global asymptotically stability of equilibrium points. So by equilibrium points, what do we mean? It means the rest points, the states at the fixed points, commonly called steady state in modeling. That is the state, and the equilibrium point is the state that describes where we discuss the disease-free and endemic equilibrium, where we are talking about the S, the T equals to 0. That means the rate of change of susceptible equals with respect to T equals to 0, or particularly the infected compartment, which is the E and the I. So I describe using this equation, the S, the T equals to f of x, and by definition, the equilibrium points could be locally or could be a disease-free equilibrium point or endemic equilibrium points. So when we say disease-free equilibrium point, it is a point at which no infection at that point, no infection persists, and the equilibrium point, the I star is always equal to 0 or the E star is equal to 0. This interpretation is that the system settles to a state where the disease is absent, and the stability of the disease equilibrium is where the disease will die out. The disease will be eradicated totally. But when you want to express in terms of R naught, it will be R naught less than 1, because where R naught is the basic reproduction number. Then the endemic equilibrium is the state where the infection persists, where and the I star is always greater than 0, the E star is always greater than 0. The interpretation here is that this maintains itself at a constant level, and it occurs whenever R naught is greater than 1. Why is equilibrium point important? Equilibrium point is the state where we discuss the steady state of a disease, and that it allows us to determine whether the disease will die out or it will persist. It helps us to also study the local stability and global stability of such a disease using either Lyapunov function method or the Jacobian method. It equally assists us to identify thresholds such as the R naught and to understand the long-term prediction of a model. Now, stability, that is where we are focusing on. We are moving to the main part of the topic. Stability is the system, in mathematical modeling, is a key concept that defines the behavior of a system when subjected to a small change in the initial condition. And a system is said to be stable if after a small a minor disturbance or a major disturbance return to its equilibrium point. But it is unstable. When it is unstable, it diverges from the equilibrium point. We have a system could be locally, it could be a Lyapunov stable, it could be asymptotically stable, it could be exponentially stable or structurally stable. And the type of stability that we have are the local stability and the global stability. When we say local stability, it refers to stability of a system within a small neighborhood or around the equilibrium point. That is when we say local. But when we are talking about global stability, it covers the entire domain of the system, the entire system. So a system is said to be globally stable if it converges from its equilibrium point from any initial condition, regardless of the magnitude of the perturbation, it returns back to the equilibrium point. Then we say it is globally stable. And with this mathematical illustration given in this equation, let me minimize this so that I can be. So anyway, let me continue. This equation where we have the norms of x of 0 minus x star less than delta, which implies that limit of x star equals as t tends to infinity equals to s star, then it is locally stable. Then it is globally stable if for every initial condition s of 0 in the domain of interest of the solution exists for all t greater than or equals to 0, then the limit of s of t as t tends to infinity equals to s star for every such initial condition. Then when x star is Lyapunov stable. When we are discussing stability, there's no way we will not be talking about basic reproduction number. That is R naught. So the basic reproduction number is the threshold parameter that establishes the local asymptotic stability of a disease and the global asymptotic stability of any disease in epidemiological model. According to Lawal, it explains the occurrence of significance of epidemic peak. Lawal et al. 2025. The many tools that are used for global stability include the Lyapunov function, the eigenvalues and eigenvectors, the linearization techniques, the bifurcation theory. But in this talk, we will focus on global asymptotic stability of both the disease-free and endemic equilibrium point of mathematical compartmental model. To do this, we will employ the Lyapunov function approach to establish the global stability of equilibrium point of some classical and case studies deterministic compartmental models. Now, Lyapunov function. Lyapunov function is the widely used method of establishing stability. It's giving a system of n order ODE, ordinary differential equation of x star equals to f of s and an equilibrium point s star. If a scalar function v, which is continuously differentiable in the domain Rn, R, is called a Lyapunov function if the following condition holds. 1. If v attains its minimum at s equal to s star. 2. Derivative of v equals to grad v f less than 0 for x not equal to x star. It means it has to be positive or semi-positive definite. Then x star equals to 0 and f of x star equals to 0. The theorem says if a function f of s is globally positively definite and radially unbounded and its derivative is globally negative, then derivative of v of s is less than 0 for all x not equal to s star. Then we say the equilibrium S star is globally stable. Is it now? Can I let me throw this open? Is it all model that can be globally stable? No, because when you carry out some analysis, for instance, if after some analysis you now get backward bifurcation, there is no need to check for global stability because once a bifurcation exists, then the model cannot be globally stable. So that is why it is not in all cases that we check for global stability. For establishing global stability, I said we use the Lyapunov function. According to Kangourty et al. 2024, there are some methods that were highlighted in that that manuscript. where the first method is the linear combination of infectious compartment. This is basically used for disease-free equilibrium. That is where we have R naught less than 1. And the form is usually V equals to, this capital V is the same thing as the V I gave using small v. I should have used capital letter V in that one too. So these formulas are very, very important, because when you are considering disease-free equilibrium, say when you are using the Lyapunov function, it is always best to use this linear combination. Also, you can also use we have the Golotzka-Fourier area, which is given according to that equation, where V equals to summation. According to that equation, we have the quadratic Lyapunov given in the other equation. So this thing, I wish I can minimize such that I will not be okay. Good. So we have the quadratic Lyapunov function, then integral Lyapunov. The integral Lyapunov, after applying it, you can see from here that is also going back to Golotzka-Fourier area. So both are applicable, but for this talk, we basically use equation 5 and equation 6. That we have the hybrid Lyapunov function too, but we will use the linear combination of infectious compartments and the Golotzka-Fourier area equation 6. Now, let's start with some examples so that we see enough stories. Let's go mathematical now. Please, we have to have pen and paper, because so that at least as I'm saying it, you'll be verifying what I'm talking about. When you consider, let's consider, I told you I'll be considering compartmental classical models. So let's consider two classical models, the SIR and the SEIR models, respectively. For the SIR model, as given in equation 11, where we have the total human population in that compartment is divided into 3. That is the susceptible, the infectious, and the recovered, as given, and the initial condition is as given to us. So now, when you want to, the disease-free is given in equation 12, while the endemic is as given in equation 13. Now, to establish that the disease-free equilibrium is globally stable, if and only if R naught is less than 1, because that is, so now to establish that, we have to the first thing you do is that you will have to write your Lyapunov function equation. That is V. If you have your global stability, always focus on the infected compartments. So that's what will determine how your Lyapunov function equation will be like. So in this one now, we have only one infectious compartment, that is the I. That means our equation will be what? V equals to Bi, where V is the Lyapunov function, B is the Lyapunov coefficient, and I is the infected or infectious compartment. So the second step is what? You will differentiate. If you say dV dt equals to B, which is a constant, then the I dt, isn't it? So now from that equation 11, we know what the I dt is. So you go and substitute. When we substitute here, then we now have B into this equation. This was the equation we have in equation 11. So from there, when we factorize out, our intention is to, according to that theorem, R naught must be less than 1. That means we must work towards getting our R naught. If you don't get your R naught, that means your stability is wrong. So now the next thing is for you to do is, if you factorize out gamma plus mu here, we have to get 1. So of course this space will be 1. If I want to factorize this one out, what do I have to do to this one? That means I have to multiply this play with reciprocal of this, such that it will be cancelled out, and it will not be as if I'm doing anything. And that's what I've done here. I factorize out gamma plus mu. When you open the bracket, then this one becomes beta times lambda over mu. Then multiply by the reciprocal, which is gamma plus mu. If I cancel this, it will also cancel this. Then if that means I have this one, this way becomes 1, and that's how I got the 1 here. So that means this is what my dV dt will now be less or equals to. Why are we putting less or equals to? Because at the feasible region, we all know how to define our feasible region. Our S is less or equals to lambda over mu. So now that's why I'm using this less or equals to sign. So because I want this, of course, this is looking like my reproduction number now, the basic reproduction number. So I cannot think of cancelling out this one since I have B here and I don't want the B to be there. So I will now, if I assume that B equals to reciprocal of this is B equals to 1 over lambda plus mu. That means the v dt will be equal to what? Beta lambda over mu into gamma plus mu minus 1, everything into multiplied by I. So since this is my R naught, then my R naught minus 1 into 1, which is looking like what I'm expecting how I'm expecting the disease-free equilibrium to be like. So that means this one is following the theorem. If R naught is the basic production number and the V equals to 0 at the disease-free, that means the disease-free master E will suffice if and only if it is negative. I mean, if and only if I equals to I star, otherwise it is negative. If I equals to I star, if this space is 0, that means everything here becomes what? Is 0. So that means it suffices. Hence, using the LaSalle invariant principle of according to LaSalle 1975, the solution of the model converges to the CP equilibrium point as t tends to infinity whenever R naught is less than 1. Therefore, we can say the CP equilibrium matka E is globally asymptotically stable. Please, I hope we all get how to derive our disease-free equilibrium for global stability. Now, let's move to how to derive the endemic equilibrium. I've told you for this lecture, we will be using the Golotka theorem, which is Golotka theorem, it's the same thing as that. According to Golotka theorem, the general equation is what? Your Lyapunov parameter into S minus S star minus S star in S over S star. This is the Golotka equation given in 6, the expansion of it. So since we have, when you are considering endemic, of course you choose the susceptible and the infectious. We are not picking the R because the R goes to nowhere. It either it dies out or it goes to nowhere. That's why we are excluding the R compartment for the endemic equilibrium. Therefore, we now have, if you take derivative of this, the same process you do for disease-free is what you will do for the endemic. Here, after writing your Lyapunov function equation out, then you take the derivative. When you take the derivative, of course, for the first one, for susceptible, we use A1 as our Lyapunov coefficient into, if you differentiate this one, if you differentiate the SDT, this will be the SDT. This is a constant. Using implicit function method, we get S star over S, the S dt. Since the S dt is common, that's why I'm factorizing it out. I will now have 1 minus S star over S into the S dt. Similarly, the same thing will occur, of course, since the equation is the same thing. That means I will now have plus A2 into 1 minus I star over I into the I dt, which is given in equation 17. Now, substituting, we know the S dt, we know the I dt from our equation, from the equation 11. So now when we substitute that into equation 17, we will now have this now. We have equation 18. As steady state, it's good to define our equation as steady state. As steady state, we have our lambda to be equal to what? If all this one moves to the right hand side, that means we have beta I star S star plus mu S star. That will be the steady state solution. And here, our gamma plus mu will be equal to what? Beta I star S star over I star. That will be the steady state solution. So if from equation 18, we can open these brackets now. If we expand, we will have equation 19. Lambda times 1, beta is times 1. So opening the bracket, we have equation 19. Please, are we all together? So now, substituting our equilibrium, our steady state solution into equation 19, we will now have this one now. That means wherever you find lambda, you substitute all these values there. Then this was the one we have before. So you do it you pick it. Normally when I'm working, I prefer to do it one after the other. Normally I can do for this one too, but to prevent too much complexity, I do for lambda first. After simplifying to a stage, I come to this one too to do that one. So that's what I've done here. I substituted for lambda, and that's why I have this equation. You can see the gamma plus mu is still there, despite that we know the solution. So now, the next thing is that I have beta IS here. I also have beta IS. What can I do such that this one can cancel out? If I equate this one to each, if I say A1 equals to A2, there are two ways to go about it. You can say A1 equals to A2 equals to something else. Then you now solve, you simplify, and then you solve as an equation. But mostly I prefer to just say A1 equals to A2 equals to A1. So that at least that one is more simple, it's not easier to expand. So setting that you now have dv/dt equals to, now wherever I have A1, I'll be putting 1. If where I have A2, please, there's no plus there. This equation is more correct. Equation 21 is more, so where I have A1, I'll put 1. Where I have A2, I'll put 1 as well. So when you now expand, you have all this for the A, this is the A1 part, this is for the A2 part. So eventually this one will cancel out. Are we there? Now, then I'm left with, I factorize out. Since, how do I do my factorization? Beta I star S star is there. If you bring it, I open the bracket. That means I will have 1. Where do I have anyone? This one looks like it, isn't it? This is beta I star S star. If I take only one, if I take one S star here, I will have one S star left. Then I have another S down. That's where that's how I got this one. Again, if you open this one, there is mu star here, isn't it? There's another mu star here. That means I will have 2. If I put mu star outside, that means 2 will be here minus. Why am I having minus? This one is mu s. I have mu star, isn't it? But I have mu here. If I put mu outside, that means I will have S star that is not existing here. That means this one will not become what? S over S star. And that's how I got this one, S over S star. Minus this one now. To get this one, we have, look at this place. I have mu star squared over S. So if I pick mu star, that means I'll be left with what? S star over S. And that is how I got this part. So eventually, this one is still available. It's not combining with anything yet. No, this one is gone. So I have only this one left now. This is not, so you bring it out. That's why I'm still having it here. And this one we cancel that from A2. Now I have this and this. Substituting for the gamma plus mu that we have here. Substituting it in equation 22, we have this one as well. Now, from here now we can have, see, when you are, how you will know that you are correct? If you have the steady state solution over the state variable, if you have S star up, ordinary S will be down. If you have S up, ordinary, S star will be down. So that will give you that you're on the right track. But once you are getting something different, you know that something is wrong. So it's better you go back and check out where the mistake is coming from. Now, from here now, using the fact that the arithmetic mean is greater than or equal to the geometric mean, it follows that 1 minus S star is less or equal to 0. This is also less or equal to 0. We can verify that when you have your arithmetic mean, that is sum of, arithmetic means sum of when you're having sum of terms over number of terms, isn't it? So it's after adding it must be greater than or equals to geometric mean. That's the multiplication root n of multiplying those n. Therefore, it follows that dv/dt is less or equal to 0 since all the model parameters are positive with equality if and only if S equals to S star and I equals to I star. This follows that the limit of S of t, I of t, tends to S star, I star. It automatically follows from 23 that R of t will also imply R star. And from equation 11, we can easily get our R star to be, let's quickly go back to, to take you back so that you see how I got my R star. So from equation 11, okay, I should be there. This is equation. This is how we got our R star. As steady state, this place will be 0. So we now have lambda I equals to mu R. So lambda R will now be equals to what? Lambda I over mu. And so it's now been lambda I star over mu. So that's how that's how I got these statements. Then we can conclude that by Lassell invariance principle, that the endemic equilibrium of model 11 is globally asymptotically stable whenever R naught is greater than 1. Please, am I making sense? Now, let's try another example. This is another classical example where we have the SEIR model. The SEIR model is where we now have, in this model now, look at model 24, we're having two infected compartments. That is the E and the I, where the E is the exposed, I is the infectious, and the R is the recovered. S is usually the susceptible. So, with the given initial conditions. So, here is the disease-free. It's not our topic for today, but to find the disease-free is always very easy. You know, at disease-free, the infected and compartment will be what? Is 0. That means the higher will be 0. Then we now have lambda over mu. That means S will be what? S star will be what? Lambda over mu. That's how we got the disease-free equation. And this way will be 0 because I is 0, E is 0. The same thing here. This will be 0, this will be 0. So, and here, since there's no infection, of course, there won't be any recovery. That means automatically the R also will also become 0. But that's not our topic for today anyway. Then this is how we got for how they got the endemic equilibrium. You can always, the endemic equilibrium is equally easy to get. Maybe some other. Now, back to our own business of the day. To establish the global stability of the equilibrium of the SEIR model 24, that is exactly stable, then we have to form, you know, I told you the first stage is what? You form your Lyapunov function equation. The Lyapunov function equation in this case, we have what? Two coefficients because we're having two infected compartments. That means V will be equal to what? A1E for the exposed plus A2I. It means when you have three infected what compartment, what will happen? You have plus A3E and so on and so forth like that. That's how it will continue. Now, the next step is what? You will take the derivative. Taking the derivative of equation 27, we have the V dt equals to A1 the E dt plus A2 the E the I dt. Substituting what we have in equation 24. You know equation 24, we know the E dt and the I dt. So, if you substitute, we have this equation now. It give us this equation. After substituting, we can see that E is here, E is also here, I is here, I is also here. So we can group them, grouping method. So we now have A1 times this one. That may become minus A1 into lambda plus mu plus alpha A2, everything into E, plus for A1 here, so we have beta S A1 minus gamma plus mu, everything to I. So that is what the equation will become. Now, setting the coefficient of E and I to 0, then we now have minus A1 of alpha plus mu plus A2 alpha equals to 0. Then we have this one too, A1 beta S minus A2 into gamma plus mu equals to 0. So I prefer to use the first equation because this one is having the state variable. So this one is more. So now using that first equation, I will now use A2 alpha equals to A1 into alpha plus mu. So simplify for that, we have A2 equals to A1 into alpha plus mu over alpha. If I say my A1 is equal to 1, it means A2 will be what? Alpha plus mu over alpha. Now, substituting that, wherever you have A1, substitute 1. Wherever you have A2, put it in equation 28. Then the equation 28 will now reduce. Of course, automatically, if you put it here, this one will go because we have A1 to be equal to 1. So wherever you see E, if you put alpha plus mu here, wherever you see A2, you feel alpha plus mu over alpha. Alpha will cancel alpha. That means we now have minus alpha plus mu plus alpha plus mu. That means this compartment will go. Then we now have the V dt equals to A1 beta S minus A2 into alpha plus mu. Please, I hope you are getting it. Now, at steady state, I mean, in the feasible region, S is less or equals to gamma over mu. In the feasible region, say pi. Now, if you put, wherever you see S, if you substitute, you know this one is already 1, so it will now be beta lambda over mu minus our A2 is what? Alpha plus mu over mu into gamma plus mu, and that's how I got this equation. Now, because I've told you our focus is to global stability is always expressed in terms of R naught. That means now you now think this is what we have. I have this equation now. If I factorize out this one, if I bring it out, what will happen to this one? That means I will have to multiply this plane with the reciprocal of what is there. That means it will now be beta lambda alpha over this one. And that is how I have this equation now. I now have beta lambda alpha over mu into alpha plus mu into gamma plus mu minus 1, because I've already taken it out. Everything to I. Since there's no any other parameter coefficient here, so this is our final result now. We now say, okay, since the whole of this plane become R naught, and if you calculate the R naught of model 24, this is what we have as our R naught. So that means this is giving us the results we needed. Thus, the V dt is less or equal to 0 if R naught is less or equal to 0. In addition, we can say the V dt equals to 0 if and only if I is equal to 0 or R naught is equal to 1. Let's check here. If R1 is equal to 1, that means this one minus 1 is what? Is 0. It means it be what? Equal to 0. So, hence, by Lassell principle, invariance principle, every solution that starts in the feasible region, say phi, converges to the equilibrium as t tends to infinity whenever R naught is less than or equal to 1. After establishing that, the next thing is for us to do what? To establish the endemic equilibrium. To establish the endemic equilibrium, I've told you throughout this lecture, we'll be using the Goff-Volterra method. So now we are dealing with 4 compartments. I've told you we always remove the R because the R is not moving to anywhere. It's either going to extinction or move to nowhere. So that means we now have S, E, I. It means we have 3 coefficients. 3 coefficients. That means we have A1 into S minus S star in S over S star plus A2. We have this equation 31. So taking the derivative of, you can see that the process is the same thing. Like the first one we did, we took the derivative. Now, taking the derivative, we have the V dt equals to, if we differentiate this one using implicit function method, we have 1 minus S star over S into the S dt. After differentiating and factorizing, that's how I got this. So the same thing will happen for the 3 of them. But we know the S dt from equation 24. So we go and substitute what we have there. Substituting, we have this equation. Now, I think after substituting, the next thing for you to do is what? Find the solution at steady state. At steady state, lambda will be equal to what? Positive of all this. Alpha plus mu will be equal to what? Beta I star S star over E star. Then gamma plus mu will be equal to what? Alpha E star over I star. That will be the steady state solution. Then using equation 31 and 32, we will now have this in this equation now. That is when you substitute and all those steady state solution, then setting. So after when you expand, we expand here. We have not expanded. If we expand equation 33, we have equation 34. Now, after having equation 34, if you set, I've told you the simplest of it is to set A1 equals to A2 equals to 1. So when we set A1 equals to A2 equals to 1, that means wherever you have, and we know the reason why we are setting it, because we have beta is in A2, we have beta is in A1. So we want them to cancel out. So when we set them to 1, we can easily cancel that out. So now, simplifying, we will have this equation now. For ease of computation, I say let this and this, since already this is what, this one cannot be simplified further. So this one and this one, let them be equal to what? Kappa. So I said let's set kappa equal to this one, because we've already got our desired result. So now our focus will now be what? All these ones now. Now, we know that alpha from here now, from this equation now, if you factorize out, there's E here, whereas we have another E here. So we now factorize out the E's and you group the E's and the highs. So by grouping, we have the kappa in plus, after grouping this, it gives me this equation 36 Now, setting the coefficient of equation 36, the E and the I to 0. Since E and I are not 0, then their coefficient was equals to 0. That's why we're setting them to 0. So now, this one, we now have this to be equal to 0 and this to be equal to 0. So we can use any of these three, since any of these two, since none of them has state variable. So now, from there, we get A3 equals to alpha plus mu over alpha. Well, we know alpha plus mu from steady state equation to be equal to what? B star, I star, S star over E star times 1 over alpha. So that means our A3 will now be what? Beta I star, S star over alpha E star. So now, and similarly, if you consider the other equation too, we will have, that means if you substitute it back to equation 35 now, no, or 36. If you substitute back to equation 36, the E will cancel out, then we now have only, the equation 36 will now be reduced to what? This one. Now the E will cancel out, then we have only the I compartment and the other non-linear compartment. So now, simplifying further, when we substitute the value of gamma plus mu, wherever you see gamma plus mu, let the value comes in there. Oh, this is not supposed to be kappa. It's a typo error there. So this is kappa, not A naught. So now, when you put kappa equals to beta IS, then this, if you substitute the value of A3 that we got in previously, if you substitute it here, so we have all these equations, substituting wherever you see A3, substitute the value, wherever you see gamma plus mu, substitute the value. Then now, expressing and collecting the like terms, those ones that looks alike, when you factorize them together, we now have this factorizing. You know, if you pick beta I star S star, let's see, beta I star S star, you know, the alpha will cancel alpha, E star will cancel E star, isn't it? I star will cancel I star. That's how we got beta S star is still there, alpha has gone. That means we have beta S star I. That's how we got this one. So cancelling out those ones that can cancel themselves, that's how we got this equation. Now, after factorizing, after cancelling out, you know, we will get this equation now. So we can now factorize those ones that are similar, sort of. If you bring this one out, this is beta I star S star. If you bring it out, that means we have 1. Whereas we have I star, we have S star here, we have I star here. That means we have 1 I star left. This is supposed to be E from, yes, it's supposed to be E, not E star. This is E. It was the I star. No, yes. This is supposed to be E. But the I star has gone. Beta I star square. Yes, it is E. Look at it here. E. This one is E. So it's beta I star S star. Beta I star. Beta I. This is I. It means I star squared is E, only E, not E star, over E star I. The alpha has gone. So this one's supposed to be E. So if you pick, that means if you bring beta I star S star out, we now have I star E over E star I plus beta I S star. If you bring it out, we have 1 minus, we have beta I here. So that means we have E star S. That's how we got E star S over E. Because we have this S star outside, that's why we are putting the S star here. So that's how we got this factor too. Since we've been able to simplify this one further too, that means, and this one, we cancel this one. So we now have K, we know K before already. This and this have been combined. This and this has already been combined. So therefore, we've been able to simplify all our equation, and it's looking in the form that means if we set S equal to S star and equals to E star, I equals to I star, then automatically the R will be equal to R star as C tends to infinity. Hence, by LaSalle invariance principle of 1975, the endemic equilibrium is globally asymptotically stable whenever R naught is greater than 1. I think the process is well understandable like that, because the process is the same thing. The first stage is what? You write your Lyapunov function. Secondly, you differentiate. Thirdly, you substitute. you expand, you get the steady state solution, then you simplify and get the desired result. Now let's go to case studies. I'll start with plant diseases. According to the plant disease, well, consider the autonomous nonlinear system of ODE governing the transmission dynamics of Cyclospora pangreae in orange plant. Previously studied by Lawal et al. 2025. The model is as given in equation 42, where the entire population was divided into 5 compartments, where we have the susceptible oranges, the exposed, the infectious, recover, and protected oranges. And the question is as given to us. So now, the disease-free equilibrium of that equation is as given in equation 43, while the endemic is given in equation 44. For further reading on how the endemic was obtained, we are advised to check Lawal et al. 2025. So, going by the theorem, that disease-free equilibrium of equation of endemic model 43 for orange model is globally asymptotically stable in the associated feasible region if RE is less than 1. So now, in this place, we have how many, in that equation 42, how many infectious compartments do we have? We have the E, the I, R is recovered, P is protected, like, more or less like susceptible. So we have only 2. That means our equation will be like the one we just finished solving. That is where we have the SEIR model. So that means the equation will be the same thing. I've only changed the coefficient. We now have B1E plus B2I. That means the process is very, very more or less the same. Now, taking the derivative, we have this. After taking the derivative, we as feasible region, the S equals to S star, which is equals to omega over num plus mu, less or equals to omega over mu. So now, when you substitute that into, that means wherever you see S, if you substitute the S star into the steady state solution into equation 45, we have this, which implies that now after expanding and collecting the coefficients, those ones that where we have the E's, when you group them together, and when we have the highs, you group them together, then you solve. We set the highs to 0, the E to 0, it gives us equation 49. Then we get the value of them. We now be left with B1 and B2. Then we get the value of B2 by making B1 to be equals to 1. Then when we do that, we substitute it back to equation to our equation. Then of course the E compartment will go. Then it will be reduced to what we have here. That's why we're having all this one here. Now, from that, of course, from our model, from model 42, we have our M, because I can see I'm using M1, M2. How do I get my M1, M2? I didn't manufacture them. Here we have mu S, I have nu S. So if I take minus S into, I will now have mu plus nun. That's my M1. This is my M2. This is my M3, as used in this place now. So I said my M1 is this. I got it from my equation. M2 is this, M3 is this, because to make it easier to write, that's why I just summarized it like that. So therefore, the V dt is less or equals to 0 if RE is less or equals to 1. In addition, the V dt is equal to 0 if and only if I equals to 0 or RE is equals to 1. And it follows that the limit of I as t tends to infinity, limit of I of t as t tends to infinity is equals to 0. So that the second and the third equations of model 42 will give what? Limit of exposed E of t as t tends to infinity equals to 0 and that. So therefore, we can establish that every solution that starts in the feasible region converges to the disease-free as t tends to infinity whenever RE is less or equals to 1. Then we can now move to establishing the endemic equilibrium. When we're establishing endemic equilibrium, of course, it's the same step you took for the other classical model that you also be taking for any other case study you want to study and you want to analyze. So you have the coefficients here. This one will be maybe C1 into the first one. We have in that place, we have susceptible, exposed, infectious, recovered, and protected. Recovered will not be there. That means we will be having we have 4 coefficients that we want to solve. So when we equate C1 equals to C2 equals to C3, why are we doing that? Let's check this model 42. this is my C1 now. This will be the coefficient, National coefficient. You don't just say C1 equals to C2 equals to, you have to think of why are you doing that. Here we have SI here, isn't it? Here we have PI, we have SI. That means C1 we can say equals to C2. This is C3, isn't it? But we don't have any one. We don't have any non-linear time here. So we cannot say C3 is equal to all this one. But for C4, we still have PI. That means we can say C1 equals to C2 equals to C4. Why this one will now be separate? That means we now have to solve for C3. Then we can say this one, and this one is equal to what? Equals to 1. So if it's equal to 1, that means we are left with, so solving it, we will now get the value for C in that equation. Now, if you take the derivative of the Lyapunov function along the solution part of model 42, it gives us what we have in equation 52. Substituting wherever we have the S, the T, and substituting them as expected, you have this equation. Then when you expand and you find the steady state, we all know how to find I've explained how to find the steady state solution. You make this one subject of the formula, then the other ones will go to this side. So that's all. We got finding the steady state solution, we were able to get equation 54. Then substituting that into equation 54 and appropriating in equation 53 as well. We simplify. After simplification, we got this equation. Consequently, when you group the common one, those ones that look alike, then I've told you for the first part, when you are doing, you do for the A1 first. So when you get the equation for your A1, the only part that is left, you come and join it with this one. Then you substitute. Do we know alpha plus mu before? You expand this one too. When you expand, you collect the like terms. When you simplify through simplification,
Sorry, it's someone just okay.
So therefore,
Dr.
using
Lawan,
the fact that the arithmetic means,
sorry, Dr.
my time is
Lawan.
past tense.
So sorry. I just want to remind you that you only have 15 minutes left. Is that all right?
Okay, yes. Okay, I'll make up.
Okay.
Thank you.
Okay, thank you.
So now we can conclude that the model 42, in the absence of reinfection, that means when there's no reinfection, it is globally asymptotically stable whenever RE is greater than 1. Then we also consider the dengue model by Abidemi et al. 2022, where they had about 8 compartmental, that is the SE, the E, the A, where S is the susceptible woman, E is the exposed woman, asymptotic woman, infectious woman, recovered woman. Then they divided their population into vector. They consider the vector population and the human population. That's why they are having about 10 compartments. So they have for that of vector as well too. That's where they have, and this is the initial condition. So the disease-free equilibrium equation is given in equation 59, while the endemic is as given in equation 60. Then the effective reproduction number denoted by RT is as given in this equation. So they follow the same process, just like the previous one that we've been solving. They form their Lyapunov equation. In Abidemi equation, we have how many infected compartments? E exposed, asymptotic, infectious. 3 for human. For vector, we have the EB, and the IV. That means we have 5. We'll be having 5 coefficients for Lyapunov. That will be A1, A2, A3, A4, and A5. You can see now. That means they have 5 infected compartments, 3 for humans and 2 for vector. That's why we have that equation 61. Now we differentiating equation 61. We have this equation as well, so that we can now solve for A1, A2, A3, and A4. And I told you, the one to set for as you want to equate to their self. When you check your equation, is it A1 and A2 and A3 that will be equals to 1, and which one are you solving for? So they follow the same process, and they were able to discuss. They concluded that the disease-free equilibrium of the dengue model 57 is globally asymptotically stable whenever the effective production is less than 1, and it is they also establish the endemic equilibrium as well. Yeah, let's discuss the stability graph. You can see that for this is for stability of disease-free equilibrium, while this is for endemic equilibrium. You can see, I mean, these are both disease-free equilibrium. Sorry, this is for human and this is for vector. You can see that it is converging to what is 0. That means R naught is less than or equals to 1. In this case, it is converging. You can see now all of them are both for the vectors and the human. They are converging to what? To equilibrium point. Similarly, if you check that of endemic, this was the endemic analysis. If you check that of endemic, yeah, this is the endemic graph too. For the endemic, you can see that it's also converging to equilibrium point. You know, the endemic, because it is greater than or equals to 1, that is why it's above the, so the equilibrium point in this case is what? Above 1. Above 0 rather. That is why you can see this is for human and this is for vector. Now, in conclusion, this lecture has highlighted the central role of global stability analysis in understanding the long-term behavior of deterministic compartmental model used in epidemiology and related dynamical systems. By employing a range of Lyapunov function techniques, including the linear and Golodka-Volterra form, we demonstrated how rigorously established the condition under which disease-free and endemic equilibrium are globally asymptotically stable. Across two classical models, that is the SIR model and the SEIR model, and the real cases where we have the orange plant diseases and the dengue disease, the result consistently show that the reproduction number and its variance serve as the key threshold parameter determining the global behavior. When R naught is less than 1, the trajectory converges to disease-free equilibrium, while when R naught is greater than 1, support the stability of endemic equilibrium. Numerical simulation further validated this analytical finding, confirming the convergence for various initial conditions. Tools and examples presented provide a robust framework for analyzing a wide class of nonlinear disease models and for guiding effective intervention strategies. Acknowledgement. I'm indeed very, very grateful to Professor Fatima Wati, who God has used to be an instrument to making this guest lecturer stuff realistic. I really appreciate, and may Allah subhanahu wa ta'ala reward you abundantly. I appreciate the Department of Mathematics of the University of Ailanga for its invitation and arrangement for this lecture. I also appreciate Dr. Abidemi Hafiz, who has helped to proofread the original lecture. Thank you so very much. May God reward you abundantly. I appreciate my PhD supervisors, my siblings, and my institution, Bamidele Olumina University of Education Science and Technology, Ikere Ekiti, and Department of Mathematical Sciences, Boesi, Ekiti State, Nigeria. Here are my references. Thank you for listening. Questions and answers are welcome. Thank you.
Thank you. And we also want to say thank you for your, yeah, right. Okay. So now we are going to the question and answer session. For everyone wants to have a question, please just raise your hand or write your question in the chat box. Is there anyone have a question for Dr. Lawal? Okay, so we have the first question from Abadi. Prof. Abadi, do you want to open your cam and ask Dr. Lawal directly, or just I read your question in the chat box? Prof. Abadi? No? Okay. So I will read the question. How to show the S minus S star minus S star ln S over S star positive definite? Do you want to answer the question directly, or you want to collect some question first, Dr. Lawal?
Huh? Either way, which style will you prefer? Should I answer it straight?
That's the first one from Abadi. How to show the S minus S star and so on.
How to
It's
show S
positive
minus
definite.
is positive definite. You have to use
Yeah.
the matrix method. You know, for every for any a symmetric model X transpose AX to be symmetric to be positive definite, it has, that means that equation must be what, equal to 0, or the eigenvalues and the eigenvalue must be also be positive. So if it is positive, that means you have to use the next matrix generation, then you now use it to solve. When you solve through your matrix method, that's why you have to show that it is positive definite. It's only through matrix method.
Is it answers the question, Pak Abadi? Or you want to continue with another question for Dr. Lawal?
Yeah, Dr. Lawal, because the fee itself is just define it, but the requirement is to be definitely positive, right? So, but we directly just choose that function. So I just want to know how to make sure that that function is definitely positive. So you cannot just use it, but you just show it how.
Can I just show how it's positive definite if I didn't get it?
Yes.
To show how, are you referring to my abnormal conditions, or which part are you referring to, sir?
We just use it as minus S star minus S star lens S over S star is just definitely positive, and you use it to prove that to prove the stability of the point, right?
Okay, let me see.
But the
If you are
requirement
trying
that
to
it is be positive first, to make sure that that will be positive first, and then you can just
it has to be
use it.
positive first, because we are discussing about population. So it can never, for instance, susceptibility cannot be negative. We can't have negative woman. So it has to be positive. Infectious has to be positive if there is any infection. Of course, it can be 0. Well, it can even, like when there's no any infection at all, it could be 0. But once there is an infection, it will be greater than that. It is positive. It is positive, definite. When all the results are positive. I don't know if you got what I'm trying to say. Because all the compartments are already positive. They can either be greater than 0 or greater or equal to 0.
So S must be less greater than S star, right?
S star can be equal to S star. That is the solution. If it is disease-free, they can be equal. And when they are equal, that means the result will be what? The Lyapunov function will be equal to 0.
Okay. Thank you.
If your S equals to S star, that means if your state variable is equal to your solution at the steady state, that means the Lyapunov function will be equal to 0, which satisfies one of those conditions.
Okay. Thank you.
Thank you, sir.
Right. Okay. Thank you, Prof. Abadi. Right. Okay. So we are going to the next question. Anyone want to answer the question? Want to have question for Dr. Lawal? All right. Maybe I will ask you, Dr. Lawal.
Yes, sir.
I just wonder about, you already show about the simple model and then go to the complex model. And now I just wonder about the more complicated model. Sometimes we also construct the model with seasonality or even environmental factor like, rainfall, temperature, or humidity. And I just wonder how might such external factor like rainfall, temperature, and so on complicate the global stability analysis. It's not easy to find. The global analysis cannot be easier to figure out about the external factor like that. And then what adaptation may be necessary to study long-term behavior in model that include periodic or stochastic forcing, something like that, Dr. Lawal?
I get the last part. Please, can you take the last part? The last statement, I didn't get it very well.
What kind of adaptation may be necessary to study long-term behavior in model that include periodic model or stochastic forcing, something like that? is it still possible to do the global stability analysis for model that include the periodic or stochastic forcing?
And yes, it depends. But if it's a condition that there's always a reinfection, there is no need for global stability analysis, because once there is reinfection, then the model cannot be stable. So it's more like, so doing the global stability for models that for disease that there's always reinfection, like measles now, like tuberculosis. So there are some models that you
I,
cannot do, there's no need to do global stability for them, because there's always room for reinfection. In that plant orange, I also gave the condition that provided there's no reinfection, because Sarcophora frangiae is common in oranges. So once there's reinfection, all those analyses prove nothing. So sometimes this is, if you know that disease that there is likely for reinfection, that infection is common in that disease, then there's no need to carry out stability analysis on it.
Yeah, right. Okay, thank you, Dr. Lawal. So here we have Mas Hasan Pandikoro. Do you want to give the question directly, Pak Hasan?
Yeah, yes, Pak Rudy, may I give a question? This is about the how to choose the suitable Lyapunov function, because I see that we have two way to construct the Lyapunov function for the equilibrium point, which is not zero. I see the Volterra function and then the quadratic function. Which one? How the way to choose the right Lyapunov function form? Because I see that sometimes we use the Volterra function and sometimes we use the quadratic function. How to see or how to identify from the model, so we will choose the right Lyapunov function. Thank you.
Yes. One, for Lyapunov function, there's no general solution for the Lyapunov function. So you can go this way, I can go this way. But what we tell you, either you're on the right path or not, is that once it obeys 3 conditions for Lyapunov function, that once I gave the condition in my slide. The first one is when it attains a maximum point at x equal to x star. The other one is when the derivative is less than 0. That is, if the derivative is semi-positive definite. And the other one is at when x star is equal to 0. Provided your solution satisfy those conditions, then your Lyapunov equation is correct, because there's no general solution for Lyapunov function, and there's no general approach. So you can decide to use quadratic method. I might decide to use integral method. You can use Volterra. I can use hybrid method. The most important thing is that it must all obey the basic rules of Lyapunov.
Okay, thank you, Professor.
Yes.
Right, okay. Thank you, Mas Hasan. So we have another participant who want to ask you the question. Mas Akbar, silakan.
Okay, thank you so much. So, Dr. Fatima, I want to asking about do you think still important the local stability? Besides, we have global
Building what?
stability.
Sorry.
Okay, sorry. So
Building.
do you think local stability is still important to do? Because we have already theorem or the way to prove that equilibrium point already stable. I mean, do we need still to do the local while we have already global?
Yes, it is sometimes, in fact, it is sometimes good to do both local and global, because local is for small disturbance, while global is for larger perturbation. So that is why it is good to establish the local stability as well.
Okay, thank you so much, Doctor.
Okay, so we still have time here. Does anyone want to ask Dr. Lawal? I think everyone already understand about your presentation, Dr. Lawal, so no need to have another question for you. Right, okay.
Where are the coefficients T and
Okay,
I?
so we have another question. Why are the coefficient E and I set to 0?
Because if we set them to 0, because if we assume that, okay, E is not equal to 0, then their coefficient has to be 0. If you have two things multiplying, if one is not equal to 0, then the other one has to be 0. So that's why we always said if E is not equal to 0, then maybe 2 has to be equal to, if, for instance, if you have 2E, and if the first one is not equal to 0, then the other one has to, because for equation, something has to equate for it, because we want to make it equation. And for it to make it equation, if one is not equal to 0, the other one has to be 0. That's why we're always setting the coefficient to 0.
Right, is that clear? Pak
Is that
Muhammad
clear?
Tafrikan? Pak Muhammad Tafrikan? Or do you want to continue with another question? All right, okay. Thank you, Pak Muhammad Tafrikan.
Yes,
Right.
yes, sir.
Anyone else? All right, okay. Thank you to all participants for your interesting question and also for Dr. Lawal for the clear and thoughtful responses. And before we close today's session, we would like to express our sincere appreciation to Dr. Lawal for sharing her valuable time, knowledge, and insight with us. And as a token of appreciation, allow me to present a certificate of appreciation on behalf of Faculty of Science and Technology at Erlangga University. The committee and Prof. Fatmawati.
Okay, thank you, Dr. Fatima Lawal, for your contribution to our webinar today. It is very insightful for us, and I hope we can continue the collaboration with you. Thank you.
Thank you, Ba.
Thank you so much, Prof. Fatma, and also for Dr. Lawal.
Thank you.
So congratulations and thank you once again for your inspiring contribution. So ladies and gentlemen, as we come to the end of today's session, let us once again extend our deepest appreciation to Dr. Fatima Lawal for her outstanding lecture. And your presentation has deepened our understanding of global stability, specifically in disease dynamic, and it has inspired many of us to explore for this fascinating field further. Right, okay. I would also like to thank for all participants for your active engagement and enthusiasm to the session. Before we officially close our session, we would like to take a group of photos together as a memory of today's guest lecture. So may I kindly ask everyone to please turn on your camera for a moment, please.
Everyone put on
Let's take a nice picture
Okay,
together.
sorry.
Oh yeah. Yeah, Prof.
Yeah, sorry, Pak Rudi. I want to ask to Dr. Lawal, could we share your slide to our participant?
Yes, ma. Yes, ma.
Hello?
Yes, ma.
Okay. Okay, I will share the slide to
Thank you.
participant via chat room here. Okay.
Right, okay, for the committee, are you ready for the screen to take a picture for that? Okay, so we are going to the first slide. Okay, go to the next slide. Done. Okay, so we are going to the next one and the last one. Right, okay. With that now, I return the floor to our Master of Ceremony to officially close the event. Thank you everyone and have a wonderful day. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam
warahmatullahi
warahmatullahi wabarakatuh. Thank you.
Thank you.
Thank you so much, Dr. Lawal.
Yes.
Okay, ladies and gentlemen, as we come to the end of today's guest lecture, Exploring Global Stability, mathematical insight and case studies in disease dynamics. Let us express our highest appreciation to our guest speaker, Dr. Omawumi Fatima Lawal, our moderator Mr. Rodianto, and Vice Dean 3 Professor Dr. Fatmawati, as well as all committee members who have contributed to the success of this event. Thank you also to all participants for your attendance, enthusiasm, and active engagement during today's session. We hope that today's lecture brings new insight and inspires further exploration in mathematical modeling and disease dynamics. With that, we officially conclude today's guest lecture. Have a wonderful afternoon and see you again in our next academic event. Wassalamualaikum warahmatullahi wabarakatuh. Thank you so much.
Waalaikumsalam warahmatullahi wabarakatuh. Silakan yang isi presensi nggih Bapak Ibu. Terima kasih semua. Thank you
Terima kasih.
Dr. Lawal. See you.
Ngisi
Monggo
presensi
Bapak
itu
Ibu.
kalau apa sih, Pak?
Thank you, everybody. I really appreciate everybody for coming. God bless you. Thank you, ma'am.
Oke, you're welcome. Monggo, tidak saya end meeting dulu kalau mau isi presensi. Bu Ida sudah ngisi presensi. Terima kasih Bapak Ibu
Sudah,
semuanya.
Bu. Tapi kan harus ada file yang diupload itu apa?
Foto ini screenshot foto ini. Screenshot foto. Ada keterangan ya tadi panitia? Screenshot
Iya.
fotonya Bapak Ibu. Presensinya bisa di-share lagi Mas Mas Akbar atau Mas Adam? Link presensi. Sampun nggak ya Bapak Ibu? Ada kesulitan isi presensi? Sudah bisa Bu Ina isi presensinya?
Ya, screenshotnya belum itu, Bu. Bentar.
Oke.